Hi everyone, with this video we are starting chapter 9. It's titled Chemical Bonding 1 because chapter 10 will be Chemical Bonding 2. So this chapter just talks about the basic concepts of chemical bonding. The picture of in the stamp that you see there is of Gilbert Newton Lewis. He is very important. He was an American chemist and he made huge contributions to chemistry in areas of thermochemistry, bonding, spectroscopy. You know, he's a really big guy, and you'll see that chapter 9, the first section, is called Lewis dot symbols. Well, it's after this guy. The sketches that you see is basically where he sketched his idea. This was on the back of an envelope for his octet rule. So let's get started. So the development of the periodic table and the concept that we just learned from chapter 7, the electronic configurations, that gave chemists basically a rationale for molecule and compound formation. The explanation, which basically was given by Lewis, Gilbert Lewis, that I just showed you the picture of, it was that atoms combine in order to achieve a more stable electron configuration. And what's the most stable electron configuration in the periodic table? It would be the noble gases. So atoms combine to form molecules and compounds so that they could be isoelectronic with noble gases. Isoelectronic means same electronic, so have the same charge as a noble gas. Remember, everything in nature does what it does so it could expend less energy. So if atoms come together a certain way and that coming together gives them a more stable configuration, then they're going to do it. So when atoms interact to form a chemical bond, only their outer regions are in contact. So remember, these things are shells. Remember, we learned about that. When we study chemical bonding, we are concerned primarily with the valence electrons of the atoms. What I'm showing you here is Lewis dot symbols for the representative elements, which is everybody but the transitions, metals, and the lanthanides and actinides, so just the representative elements, and the noble gases. The number of dots corresponds to the number of bonds an atom of that element can form in a molecular compound. In other words, the number of dots is how many valence electrons that atom has. Remember, valence electrons are the outermost electrons, those electrons in the outermost shell. Everything that's not a valence electron is called a core electron. And you see that there's a clear pattern that forms with people in the same columns. Everybody in column 1 all has one valence electron. Everybody in column 2 all have 2 valence electrons. Everybody in column 7 has 7 valence electrons. The similarity of these valence electron configurations, if you're in the same column, is what makes the elements in the same group resemble one another in chemical behavior. We've kind of touched over that throughout the semester. Now is when we're really going to start understanding why certain things form what they do. Just to make sure we understand how to do these Lewis dot symbols, let's try to write the Lewis dot symbol for the following species. First one is calcium. Calcium sits in the second column, so you would have calcium with 2 dots, since there's 2 valence electrons in calcium. Next, lithium, but it's not just lithium neutral, it's a lithium cation. So it has 1 less electron than what lithium would normally have. So where's lithium? Lithium is in the first column. So normal lithium has 1 dot, 1 valence electron, but it's saying that it's the cation of lithium. So basically what you would do is you would put lithium plus, leave it like that, or you could also put helium in brackets, because lithium plus has lost 1 electron, which means electronically it's the same thing as helium. It's isoelectronic to helium. So you can put helium in brackets and that would be okay as well. Next one, phosphorus. Well, phosphorus sits in the 1, 2, 3, 4, 5, 5th column. So it has how many valence electrons? It should have 5. So you put 5 dots around phosphorus. 1, 2, 3, 4, 5. Easy. What about the last one? P3 minus. So now this is the anion of phosphorus. It's gained 3 more electrons. Okay, so phosphorus neutral has 5. So if I've gained 3 more, I'm going to have 8 electrons. So I put 8 electrons or 8 dots around phosphorus, which equals argon electronically, because 8 electrons is like saying the same thing as you are argon. You are isoelectronic with argon. So you can also just put argon in brackets. That would be okay as well. But P with 8 dots is good too. All right, let's move on. So here we have the ionic bond, and we have heard of ionic bonds before, and we know that ionic bonds are transfer of electrons versus covalent bonds, where those are the guys that share electrons. But in chapter 8, you should have read that elements with low ionization energies tend to form cations. Like those alkali metals in the first row, they tend to form cations. And elements with high electron affinity, basically they want electrons. If affinity means I like electrons, so high electron affinity tend to form anions. Those are like the halogens. In an ionic bond, there's, like I said before, there's a transfer of electrons. And remember, the entire goal for these compounds to do this is all to get to the happiness of a noble gas. So lithium has a really, really low ionization energy, so it tends to lose electrons quite easily. And fluorine has a really high electron affinity, so it tends to accept electrons quite readily. You notice the goal here. So you start out with lithium, neutral lithium, and that has 1 valence electron, so it has 1 dot. And on the bottom, I'm just showing you what the electron configuration would look like. So it's 1s2, 2s1. And then you have a fluorine, which has 7 valence electrons. And the complete electron configuration is 1s2, 2s2, 2p5. But the valence electrons is just the last electrons in that last shell, which is 2s2, 2p5. That equals to 7 electrons. So that's why fluorine only has 7 dots. When you combine these two together, the whole point is to be isoelectronic with a noble gas. So since this is an ionic bond, you have a metal and a nonmetal coming together, there's going to be a transfer of electrons. So lithium, since it has a really low ionization energy, it's going to give up its electron to fluorine. In essence, what that means is that lithium becomes isoelectronic with helium because it's missing 1 electron. And fluorine has essentially gained an electron that was given to it by lithium, so now it's sort of the same electronic charge as neon. So the new, electron configuration, once these two elements have combined, is 1s2 for lithium, which is Li+, and 1s2, 2s2, 2p6 for fluorine anion, which is, of course, F-. Let's try another example. We have calcium and oxygen forming calcium oxide. This is also an ionic bond. It's a metal and a nonmetal. When we do these problems, make sure that it's balanced, but this one is. We have to assume that the diatomic oxygen splits up. Okay, so really what you're dealing with here is a calcium and an oxygen. So calcium has 2 valence electrons because it sits in the second column, and oxygen has 6 valence electrons. So what you're going to do is you're going to basically transfer over 2 electrons from each calcium to 1 oxygen. In essence, giving calcium a 2+ charge and oxygen a full octet, a 2- charge. So essentially, the calcium becomes isoelectronic with argon, and oxygen becomes isoelectronic with neon. See, everything happens just so they can become the same electronic charge as a noble gas. That's the entire purpose of everything here. Let's do another example. This is example 9.1 in your chapter. It reads, use Lewis dot symbols to show the formation of aluminum oxide, which is Al2O3. Assume the oxygen breaks up first. Okay, so aluminum oxide comes from aluminum and oxygen, atomic oxygen, obviously, because it's telling us to break it up first. So let's first write the reaction. It's aluminum plus oxygen, O2, yields aluminum oxide. Well, this is not balanced, so we have to balance it. 2 moles of aluminum plus 3 moles of oxygen yields 2 moles of aluminum oxide. What is the Lewis dot symbol for aluminum? Aluminum sits in the third column, so it has 3 valence electrons. The electronic configuration of aluminum is 1s2, 2s2, 2p6, 3s3. What about oxygen? Oxygen has 6 valence electrons, and its electronic configuration is 1s2, 2s2, 2p4. When it forms into aluminum oxide, there's only 2 aluminums and 3 oxygens that come together. You have to do a little bit of drawing here, but 2 electrons from 1 aluminum will be transferred to 1 oxygen. Then the other electron is going to be transferred to the second oxygen. Now you have 1 more aluminum you're left with. So you take 1 aluminum out of those 3 to fill up the middle oxygen, and then you have the 2 remaining electrons in that aluminum going to the last oxygen. So you see there's a total of 3 electrons in each aluminum that have been transferred to these oxygens. At the end, you basically have an aluminum that transfers, well, 2 aluminums, but each aluminum transfers 3 electrons, and each oxygen receives 2 electrons. Isoelectronically, aluminum looks like neon, and oxygen also looks like neon. The new electronic configuration of aluminum in aluminum oxide is 1s2, 2s2, 2p6. The new electronic configuration of oxygen in aluminum oxide is the same thing, 1s2, 2s2, 2p6. Alright, that's it for this video. I am going to pick up with covalent bonds in the next video. See you later.